There are 3 fan laws. They take about a minute to learn, and they will save you from most of the expensive mistakes people make with fan speed. The reason they matter is that our intuition about speed and airflow is wrong, and it is wrong in the direction that burns out motors. Here they are. Change the speed of a fan and airflow changes in direct proportion. Pressure changes with the square of the speed ratio. Shaft power changes with the cube. Flow to the first power, pressure to the second, power to the third. 1, 2, 3. Let us make that concrete, and let me be clear that these are illustrative numbers chosen to show the arithmetic, not a specification for any product. Take a fan running at 1000 revolutions per minute, moving 3000 cubic meters per hour at 200 pascals, and drawing 1 kilowatt at the shaft. Now speed it up by 20% to 1200 revolutions. Airflow goes up by that same 20% to 3600. Pressure goes up by 1.2 squared, which is 1.44, so 200 pascals becomes 288. And shaft power goes up by 1.2 cubed, which is 1.728, so your 1 kilowatt becomes 1.73 kilowatts. You asked for 20% more air. You are drawing 73% more power. Run that backwards and you get the single most useful fact in fan energy. Slow a fan down by 20% and you keep 80% of the airflow, but shaft power drops to 0.8 cubed, which is 0.512. You are using barely half the power for 4/5 of the air. That is the entire physical basis of variable speed control, and it is why part load operation is where the savings live. Now the trap, and it is the reason motors fail. If you speed a fan up because the airflow is disappointing, the power demand rises with the cube while the airflow you gain rises only in proportion. A modest speed increase that looks harmless on the airflow chart can push the shaft power past what the motor was sized for. Always check the cube before you change a pulley or raise a set point. There is a second family of fan laws for changing diameter rather than speed, and the exponents are different, so do not mix them up. For geometrically similar fans at the same speed, flow goes with the cube of diameter, pressure with the square, and power with the 5th power. That 5th power is why a modest increase in wheel size has such a dramatic effect on the motor you need. Now the conditions, because the laws are exact only when they hold. The fan must be geometrically similar, which is automatic if it is the same fan at a different speed. The system it works against must not change. And the air density must be the same, because every one of these quantities except volume flow depends on density. That density condition is the one that catches people in the field. The fan laws describe volume flow, cubic meters per hour, not mass flow. Move the same fan to altitude, or run it on hot air, and it still shifts the same volume, but the air is thinner. The pressure it develops and the power it draws both fall in proportion to density, and if your process actually needed a mass of oxygen or a quantity of cooling, you are now short even though the fan is doing exactly what the catalog says. Here is the practical implication for anyone commissioning. If the measured airflow is low, do not immediately reach for more speed. The laws tell you what speed will cost, but they cannot tell you whether the problem is speed at all. A blocked filter, a closed damper, a fan running backwards, or an axial fan install will all produce low airflow, and speeding up an unhealthy system just moves you further along a curve you should not be on. Use the laws in the other direction as a sanity check instead. Take your design point, apply the ratios to your measured speed, and see whether the airflow and power you are actually measuring are anywhere near what the laws predict. A large discrepancy is telling you that one of the 3 conditions has been violated, and finding which one is the real fix. So the summary is short enough to remember. Flow with speed, pressure with speed squared, power with speed cubed. Valid for the same fan, the same system, the same air density. Check the cube before you speed anything up, and remember that the cube is also a promise when you slow down. If you are looking at a variable speed retrofit and want to know what it would actually save, the fan laws give the shape of the answer but not the number. That depends on how many hours you spend at each load point. Send your duty profile and we can work through it against the curve rather than quoting you a percentage.